So now let us look at the geometric meaning of differentiation. It is on the graph y is equal to f of x. So if you differentiate this curve at the point x is equal to a, what does the differentiation mean on this graph? So I'll give you the final result. So the value of differentiation at x is equal to a gives you the slope of tangent to y is equal to f of x at x is equal to a. So this is the geometric meaning of the differentiation of the function at x is equal to a. So let us see why this is happening. So now, what is the differentiation of f at x is equal to a? That is rate of change of y with respect to x at x is equal to a. So previously we have understood differentiation as the rate of change. Now if you take the points a and b, a has the coordinates a and f of a, and as you move h units forward, b has the x coordinate a plus h and the y coordinate f of a plus h. So what is the slope of secant AB? So you can think of the secant as a straight line. So what is the slope of this straight line? So we know the 2 points on this straight line. So what is the formula for slope of a straight line? y2 minus y1 by x2 minus x1, right? So the slope of the secant AB is y2 is f of a plus h minus f of a by x2 minus x1, a plus h minus a is h. So delta y by delta x, change in y by change in x between any 2 points gives you the slope of tangent. Slope of secant between those 2 points. Now, what happens if we go from delta y by delta x to dy by dx? So, what is dy by dx? Dy by dx is nothing but limit h tends to 0, f of a plus h minus f of a by h. This is what we have already seen. So, what happens if you take this h and make it very small? So as you decrease the value of h, that means the value of x coordinate of the second point is coming closer and closer to the first point. So let us bring b here first. Let us bring b out closer, still closer, so on. So as you bring x closer, obviously y also becomes closer because x and y are related. So now instead of b here, if you have b somewhere here, so this line looks like this. This line looks like this. So as you can see, this line looks more like a tangent at x is equal to a. And if you bring this b still closer to a, the limiting case of secant will become a tangent at x is equal to a. So the slope of secant AB as h tends to 0 becomes slope of tangent. Slope of tangent at x is equal to. So graphically, differentiation at x is equal to a means the slope of tangent to that curve at x is equal to a. Now if a particular tangent, if a unique tangent exists at x is equal to a, then we say that the function is differentiable at x is equal to a. More specifically, a unique and non-vertical tangent, if it exists at x is equal to a, then we say that the function is differentiable at x is equal to a. Why am I saying non-vertical? Because vertical lines have slope is equal to infinity. So we want a finite slope of tangent. So if differentiation exists, that means you need a tangent with a finite slope. So if that exists, then the graph is differentiable at that point A. If not, it is not differentiable. Now, once you understand this geometrical interpretation, we'll try to see the different cases where the function will become non-differentiable. So geometrically, that is graphically, so to see whether a function is differentiable at a point or not, you need to look for two different cases. So look out for sharp edges on the graph. So if a graph contains sharp edges at some point, that means the function is not differentiable at that point. So as long as the function is smooth, as long as the function looks smooth, the function is differentiable. For example, if you have a sharp edge like this, so it is going like this and suddenly it has turned and the further graph is like this. So this is a point where f of x is not differentiable. It's not differentiable at this point A. So you can see why this is happening very clearly. So at this point A, so if you look at the tangent, the slope of tangent drawn from the left side. So here the tangent from the left side will look like this, right? And the slope of this is positive. And if you come from the right side, the tangent will look like this. Tangent will look like this. So from the left side the tangent will look like this. From the right side the tangent looks like this. Right? Hence, you have different slopes of tangents on different sides. That means the right differentiation is different and the left differentiation is different. Hence, the function is not differentiable. So wherever you have sharp edges on the graph, the function is not differentiable. So this is the single most important distinction by which you can find whether a function is differentiable or not. For example, if you have a mod x function, the graph of mod x looks like this. There you have a sharp edge at x is equal to 0. That means mod x is not differentiable at x is equal to 0. So whenever you have a piecewise function also, you have to look for sharp edges at the boundary points. So if you get a sharp edge, it is not differentiable. No sharp edge, it is differentiable. The second problem that you get is look out for discontinuous points on the graph. So if a function is discontinuous, it has to be not differentiable. So discontinuous implies not differentiable, because if a function is discontinuous, that is if you have something like this, you have a function which looks like this. So at x is equal to a, x is equal to a. So if you have limit h tends to 0, f of a plus h minus f of a by h. So if you carefully observe this limit, the denominator always tends to 0. So in the denominator you have an infinitesimal quantity. So for this limit to be finite, in the numerator also you should have an infinitesimal quantity. That is, f of a plus h has to tend to f of a. That is, if you go slightly towards the neighborhood of a. So f of a is the exact functional value at x is equal to a. F of a plus h is the functional values on the neighborhood of a. So these two should not differ by a finite quantity. That is, f of a plus h should tend to f of a, which is the condition for continuity. So here f of a is this, f of a plus h, that is in the neighborhoods, the functional values lie here. You have a finite difference between these two. That means the numerator is finite, the denominator is infinitesimally small, and this becomes infinity. So whenever, even if the function is like this, if you have a function going here and like this, so here also the functional value is somewhere here, but if you go towards the left neighborhood of A, the functional values lie here. And the difference between these two, as you can see, becomes finite. So whenever the difference between the functional value and the values in the neighborhood or the limiting value is finite, the function is not differentiable. So if f of a plus h is different from f of a, that is limit h tends to 0, f of a plus h is different from f of a. That is, if the condition for continuity is not valid, then the function cannot be differentiable at that point. So not continuous directly implies non-differentiable. That means if a function is differentiable at a point A, it has to be continuous. So differentiable, these are very important things you need to understand. Differentiable implies continuous. Not continuous will imply not differentiable. If a function is continuous, it does not imply differentiability. So differentiability implies continuousness, but continuousness need not imply differentiability. That is, if a function is continuous, it need not be differentiable. Sometimes it can be differentiable if there is no sharp edge. Sometimes it is not differentiable if you have a sharp edge. So I hope you understand how to check whether a function is differentiable or not from the graph. And you should have also understood how to differentiate, how to find if a function is differentiable or not analytically using the condition. So limit h tends to 0, f of a plus h minus f of a by h should be a finite quantity.